Let's dive right into today's explainer. We're going to track exactly how 3D printing grew up. It started out as this niche prototyping tool, and now it's a powerhouse technology, printing rocket engines, sustainable houses, and, believe it or not, living human tissue. Additive manufacturing has literally rewritten the rules of how we build the physical world around us, and today, we're going to unpack exactly how that happened and where it's all heading next.
We've got a seriously incredible journey ahead of us today. We'll kick things off with the additive manufacturing revolution, break down the technologies and smart materials, and look at how it's transforming the physical world. Then we'll get into the miracle of bioprinting, do a reality check on the economics, environment, and ethics, and finally, look at the future of 3D printing.
Section 1. The additive manufacturing revolution, from concept to reality.
To truly grasp why this is such a revolution, we actually have to flip traditional manufacturing completely on its head. For centuries, we've relied on subtractive manufacturing. That's basically like sculpting a block of marble. You cut away the material you don't want, which obviously creates massive waste. But additive manufacturing? That's more like building up a highly intricate form using clay. You're starting from absolutely nothing and adding material layer by precise layer, only putting it exactly where the digital blueprint says it needs to go.
It's wild to think about how fast this tech is accelerated. I mean, we go from Dr. Kodama's UV resin concept back in 1981 to Chuck Hull actually printing the very first physical object, which was just a simple little eyewash cup, in 1983. The tech kind of quietly matured in industrial labs until 2005, when the open source RepRap project kicked off a massive consumer boom. Fast forward to the mid-2020s, and those early desktop novelties, they've evolved into heavy-duty, mission-critical manufacturing for the aerospace and nuclear sectors.
Section 2. Technologies and Smart Materials. Let's open up the 3D printing toolkit.
Okay, so here's the really crucial point. Whether you are printing a cheap little plastic toy or a highly complex titanium spinal implant, you follow the exact same, universal 5-step workflow every single time. You start by creating a 3D model, convert it into a format the printer can read, and then you slice it. Slicing mathematically cuts your digital model into hundreds, sometimes thousands, of horizontal layers to generate the exact toolpath instructions. Then the machine actually prints it, layer by layer. Finally, you post-process the object, which could mean washing away uncured resin, or even heat-treating a freshly forged metal part. And of course, different technologies solve completely different problems. FDM is probably what pops into your head when you think of 3D printing, extruding melted plastics for quick prototypes. But if you need extreme microscopic detail for something like a dental crown, you'd use SLA, which cures liquid resin with a UV laser. For tough, functional parts, SLS sinters nylon powder together. And right at the bleeding edge, you have SLM, which literally uses high-powered lasers to melt titanium and aluminum powders for aerospace and medical implants.
Section 3. Transforming the physical world. Let's look at the industrial applications reshaping 2026.
Take GE Aviation's LEAP engine fuel nozzle, for example. This specific part is a total legend in the industry because it perfectly proves why this matters. GE took what used to be 20 separate brazed pieces and 3D printed them as one single unified component. The result? It's 25% lighter and 5 times more durable. In the aerospace world, where every single gram of weight translates to massive fuel savings over an aircraft's lifespan, that isn't just an improvement, it's an absolute game changer.
And the sheer scale of adoption across different fields is just staggering. We aren't just printing simple brackets anymore. Space agencies are printing rocket engine combustion chambers. Construction companies are using giant robotic arms to extrude concrete for sustainable houses, and even testing lunar habitats. In medicine, surgeons are dropping in custom-printed titanium cranial plates. Formula One teams are literally printing new aerodynamic parts between races. We're even printing food, specifically nutrient-dense, soft-texture meals for hospital patients to help them swallow safely while preserving their dignity.
So, it's absolutely no surprise that the global 3D printing market hit a whopping $29.3 billion in 2025. That massive valuation is directly driven by these industries shifting away from just using printers for quick mock-ups and relying on them for high-volume end-use manufacturing.
Section 4. The miracle of bioprinting, the ultimate frontier.
So here is the big question. It's an amazing rhetorical pivot, really. We've totally mastered printing the inanimate. We can print the strongest metal alloys on Earth, but can we actually manufacture living, breathing tissue? The secret to pulling that off comes down to one thing: bioinks. If you want to print life, you obviously can't use melted plastic or metal powders. You need highly specialized, water-soluble mixtures that actually contain living cells. These bioinks use natural biomaterials like collagen to act as a scaffold. The biggest hurdle here is keeping those delicate living cells alive. You have to protect them from the intense physical stress of being squeezed through a tiny printer nozzle, and then immediately give them the structural support they need to survive, multiply, and eventually grow into functional tissue. And we've already seen some mind-blowing milestones, like researchers at Tel Aviv University successfully printing a miniature, rabbit-sized heart using a patient's own cellular tissue. But there's a massive roadblock keeping us from full-sized human organs. To keep thick, dense tissue alive, it needs a constant supply of oxygen. And to do that, you have to print microscopic capillary networks, which are about 5 micrometers wide. Achieving that extreme level of vascularization, that remains the absolute holy grail of bioprinting today.
Section 5. Economics, Environment, and Ethics. Time for a 2026 reality check.
Let's talk money, because the economics are shifting rapidly. As of 2026, the cost per part for industrial 3D printing dropped by an astonishing 40% compared to just 3 years prior. This massive drop in production cost is the exact tipping point making additive manufacturing truly competitive with traditional injection molding, especially for short and medium manufacturing runs.
Now, environmentally speaking, it's a genuine double-edged sword. On the plus side, we're slashing raw material waste by up to 90% simply because we only print what we actually need. We're creating lighter parts that save tons of fuel in aviation and enabling local production so we don't have to ship parts across the globe. But on the flip side, we have to honestly confront the massive electrical demands of those metal melting lasers. Plus, we've got to manage hazardous chemical resins and deal with air quality concerns from the nanoparticles released when melting certain plastics.
And the technology forces us to navigate completely uncharted legal waters too. Think about it. When you can seamlessly scan and print any physical object, intellectual property security becomes incredibly tough to enforce. We're also seeing intense, ongoing debates over undetectable 3D printed firearms, impartially balancing Second Amendment rights with public safety regulations. And as bioprinting advances, well, we are heading straight into deep philosophical debates over the moral status of manufacturing and owning living human tissue.
Section 6. The future of 3D printing. The horizon of manufacturing.
Looking at the cutting edge right now, the new normal gets pretty sci-fi. We've got volumetric bioprinters that use intersecting light projections to cure entire 3D objects all at once in mere seconds, rather than slowly building layer by layer. We're stepping into 4D printing, where materials literally shapeshift over time, reacting to heat or moisture. Space agencies are actively testing how to print off-world structures using local lunar dust, and we're seeing militaries and energy grids print critical replacement parts right there in the field, exactly when they need them.
Which brings us to this final, really profound thought. Additive manufacturing has evolved from a clever little prototyping trick into a force that fundamentally alters the boundaries of what's physically possible. We are literally turning our digital imaginations into tangible reality, layer by layer. So I'll leave you with this. When we have the ability to instantly manifest our digital ideas into the physical world, how is that going to reshape your own life tomorrow?